Okay, so good morning to you, everybody. It's a pleasure to see so many being interested in this subject, which I think in the future more people will be interested in, not only for optimizing SCS orbitals, but in general. I think this gradient enhanced Kriging has its future for it as a replacement for traditional Newton-Raphson optimization. It is our pleasure this morning to have Daniel back here with us. You spent the whole fall with us, didn't you? When did you come? In January or February?
I think it was May, and
May?
then I think
So
I'm
you
there
were
for
just
Yeah, it was a couple of months.
three
2 or 3 months.
months. Okay. And you did a collaboration within the Erasmus program with us.
Yeah, I was an Erasmus student, and then I came from Cologne to Uppsala.
So
Really nice
is
experience.
this something you recommend people getting this experience?
Definitely.
Oh,
So
well, that's I'm pleased
Uppsala
to
in
hear.
itself is a great city already.
I'm pleased to hear that. Uh, I'm sorry. I mean, Cologne is a city with a big dome. Uppsala is also a city with a big dome. It's not a big city with a dome. So I apologize for you having to downsize with respect to that. All right, enough fun here. This morning you are supposed to, or I kindly asked you to, and you kindly agreed to give a oral report, which is not a part of what's mandatory, but we think it's so exciting, the stuff you've been doing, so we would like to hear about it and share with others. So with no further ado, we look forward to your report, which you have entitled Subspace Gradient Enhanced Kriging, a superior SCF optimization method. Please.
Yes. And with that, I'm going to share my screen with you. So let's start with that. All right. So welcome also from my part to this little presentation about subspace gradient enhanced Kriging. I titled it a superior SCF optimization method, and let's see about that. So first, a bit of background. I hope you can see my cursor. Maybe I can do it with the laser pointer. Yes, right here.
We can see it.
All right. So a little bit of background. Gradient enhanced Kriging was first introduced in quantum chemistry as a geometry optimizer or geometry optimizations, of course. This you can see here in this first paper published by Roland Lin's group and co-workers. And then he made the switch also to SCF optimization, which is here given in this paper already. So there's going to be a new paper, I think, soon. But it was already published here with Subspace Gradient Enhanced Kriging. And here it was already done with RS-RFO, which you can see here as an underlying second order method. So, of course, we are always talking here about the SCF procedure. So let's talk a bit about the notation or the terms I'm going to use here. So in the SCF procedure, we are doing a progress towards the minimum of the energy, which is at the end here. But first, we're making an initial guess. And then far away from the minimum, we first have a prelude. I call it a prelude, but it's actually just the SCF startup with different robust methods that work well in the non-quadratic region. And then at some point, we're going to switch to a second order method. And this is exactly what it's done in this paper. And my first task was to switch out this RS-RFO, which you can see here as different iterations, here marked as this dark green tone. And what also was done is to lay on top this subspace gradient enhanced Kriging for each iteration. So these methods are connected. And my task was now to switch out RS-RFO to different second order techniques, such as DIIS, which is the most prominent second order optimizer for self-consistent field, and also BFGS, which is a bit more of a general optimization technique. So it's a quasi-Newton method. And the reason for that is that RS-RFO is much more costly than the other two methods here. So my task was to do this also for these two methods. And then the second task was to omit the prelude, because the motivation for that was that gradient enhanced kriging is not a second order method. So we hope that we could just start it from the beginning. So maybe it's also a good method right from the beginning. So, and with that, let's talk a bit about theory. So we're going to switch from this horizontal point of view to this vertical point of view. So we have again this second order method and this kriging. And now in this typical flow chart, we would write here these iterations as these arrows. And of course, in the beginning, we had the initial guess and the prelude. So questions that might arise here are, what is the actual framework? What are we optimizing? And how are these two methods here connected? They somehow have to be connected in order to give the information forwards. And then what is even gradient enhanced kriging, and especially subspace gradient enhanced kriging? So let's get a bit of theory under our belt. Of course, we are in quantum chemistry. So we start off with the Schrödinger equation. And then we are here now in the Hartree-Fock theory for SCF. Of course, it's also, or it can be used for DFT, but I'm going to mainly talk about Hartree-Fock because that is what I benchmarked. So in order to get this Hartree-Fock equation here, we have to have an ansatz for this wave function, which is then a single Slater determinant, not multiple, as in cases where we would simulate also electron correlation. So we just have here a mean field of the electrons. And the second part that we need is the variational principle. And with just that, we would get these Fock equations. But they are a little bit hard to optimize because here we would have actual functions, but that's not easy for a computer to optimize. So we introduce a basis where we have a linear combination of atomic orbitals to generate these molecular orbitals here. And what we are mainly interested in here is the coefficients. So the basis we already know, there's no information to gain here, but these coefficients are interesting. And from this equation, we would then get a matrix equation here with this Fock matrix, the coefficient matrix, the eigenvalue or eigenenergy matrix, the overlap matrix. And this would then be a matrix eigenvalue problem, at least when we get rid of this overlap matrix here. And the problem with that is that these two matrices actually are depending on each other. So after we solve this equation, we actually haven't solved it because this Fock matrix here actually changed under this change of this coefficient matrix. So we have to solve it iteratively. And this is what is defining the SCF. So how do we actually optimize it? We could do this matrix solving technique over and over again, but there's actually developed a much more efficient approach where we make use of calculus. And in order to make use of calculus, we actually have to have some kind of parameter that we can vary. And for that, we have to do a parameterization. And this is what is shown here with this equation. So we can first write this here, the wave functions here, Slater determinant, as a product of creators. So these creators here just act on the orbitals and so that the orbitals get introduced into this wave function. And then we can write this kappa here, which is now our new parameter, so to say, for a position as this combination of creators and annihilators, and together they are substitutions. So with that, we can actually change the Slater determinant. And here's the actual parameter that defines our space. Exactly. And to get now back from this operator point of view to this matrix point of view, we get here an antisymmetric matrix, which defines our position in this energy space of electronic optimization. And here, this is represented by this matrix. And actually, it just has values in this occupied virtual block. So we only change occupied and virtual orbitals. And these occupied, and virtual blocks are actually 0. Because there it would just be unitary transformations, and the Hartree-Fock is invariant to that. And then if we put this antisymmetric matrix into an exponential, we actually get an orthogonal matrix. And this matrix leaves the length invariant. And this makes sure that the orbitals always stay orthogonal to each other, which is very important in this optimization. And now after we introduce this parameter, we can make use of the calculus, as I said. And so we can do a Taylor expansion. And here of second order, doing more orders would just be too costly. And yes, so we have here a gradient, which is directly defined after we have a Fock matrix, the Fock matrix by these elements, or this from the occupied virtual block. And also we can get an initial guess of the Hessian, not initial guess from the SCF in the beginning, but just an initial Hessian per iteration. And this can also just be from the Fock matrix. All right, and with this second order Taylor expansion, we can define the Newton step, from which we can get a displacement to get from one iteration to the next iteration. So if we have for one iteration the Hessian matrix or an approximate of that, and a gradient, we can get or use this formula here and get a next displacement. This formula actually is analytically derived from if we have a quadratic function, we would actually directly step towards the minimum. But of course, we are not just have a quadratic function, but it's much more complex. So if we're not in the quadratic region, we would have an error, and that's why we need multiple steps. Okay, with that, we actually got some questions answered. We are doing direct minimization, so that's what it's called with this, actually directly changing these parameters. And we also see how the second order method, which uses this step, so this step equation here, in some way or another, so it actually produces a displacement, and this is how the second order method and Kriging is connected. So let's see how this Kriging uses this displacement, and let's see what is Kriging even. All right. So the main equation of gradient enhanced Kriging is this here. And here I first need to point out that this is a surrogate model. So this energy here doesn't or necessarily have to be an actually energy in the Hartree-Fock, or which is directly connected to a Hartree-Fock energy, but it is going to be a reasonable energy. And we also have here this dependence on the positions in this space. This here is the trend function, which makes sure that we are in the right range of energy. So it makes sure that we are bounded from above. And this product here is a weighted sum, depending on what you multiply out first. If you multiply out these vectors first, then you get the weighted sum of energies. So it's kind of like a linear combination of energies. But you could also say you want to first multiply these out, and then you would have a weighted sum of Gaussians. So let's get into a bit of detail here. What are these three variables here, or matrices, vectors? So this first one here, this y is the data vector, and it really defines the information that we access from the Hartree-Fock or the SCF into this surrogate model. So it defines really our surrogate model. So it stores the actual energies with their positions and also with their gradients of the previous m iterations. So during the SCF, we have multiple iterations, and at some point we make this Kriging and use all the iterations from before. At least most of, or some of them. All right, this M here is the covariance matrix. And if I would describe it in one sentence, it would take care of the redundancy between these data points that we put into this Y. So what do I really mean by redundancy? Let's say we have these points already, which are in this Y vector with these positions here. Let's say this is the X-axis, and in the Y-axis we would have the energy. Then if we have 2 points far away, I would say they are not really redundant. They are giving information from different parts of this space. So they have different gradients, and they really get important information into this model. But let's say we are really close, then I would say there's actually high redundancy. They are not really bringing more information into the model, and we really need to take care of that in this gradient enhanced Kriging. So what does it actually mean to have this redundancy, or how do we actually do this in a computer, so to say? We introduce a metric, and this can just be thought of as a distance, just a scale for how far points are away, or just numbers. And this is the formula that we are using. And if you pay close attention, then this would actually be very similar to the Euclidean matrix. So if we have 2 points in space, then the distance would actually be just the difference of the different points of the vectors. Yeah, and then we also divide here by a characteristic length, but I don't really want to go into detail here. Just a note that this also depends on the eigenvalues of the Hessian here. Okay, now we have a metric, but it's really just a number for how far away something is. But to actually evaluate how far it is, or to define what does it really mean that the points are close, we have a covariant part here with the covariant metric now, and I would define or describe it as the closeness. So this is here a function that gets this metric value for these points here, and then this is just a Gaussian type of function. So this would define the closeness, and then we put all these function values now after we put these positions in for the different positions in these matrices, or in this matrix and also in this vector here. So how do we really do this? Just briefly. So we now have a vector of different positions, and then we do this for all the positions. And this is just the first element of this covariance matrix. This would just be Kriging with this matrix, and with gradient enhanced Kriging, we also have these rows and this matrix of matrices. And these are the first and second derivatives of these covariance functions. All right, I also said that we put this closeness, so to say, in this vector here. And I would call it the exploration vector, because here are the parameters inside that we actually vary to explore the surrogate model. You could also call it the closeness vector, because it also just takes these covariance functions inside, and then this again would just be for Kriging, this one vector here, but it's actually a vector of vector because we're doing gradient enhanced Kriging, and then again we have this first derivatives. So to make sure you understand this closeness, if we now want to explore this model, we would have a new point, which we want to get. And with this vector, we make sure that energies that are far away have a low contribution to this new energy, and points that are close by have a higher influence on this energy. So with that, I explained this gradient enhanced Kriging equation. But there's actually a problem for SCF because this parameter here is actually extremely large. So it is as large as the number of occupied orbitals times the number of virtual orbitals, and this easily gets over 10,000 numbers, but actually it can just be as high as it can get, so millions of parameters inside. And that's why we have to introduce a subspace, and this just has the slogan, make it small, this space. And how do we do that? So we have to choose the basis for the subspace really wisely. So what do we need? We actually need the vectors that point towards the minimum to really get this information out that optimizes the SCF. And these are the displacements from the previous iterations and also the gradient displacements. And we add to that the current gradient of the iteration that we are in, and also this displacement we get from the second order method. So this is where we put this delta kappa in that I talked about before from the second order method. So this is the actual connection. All in all, this would have a basis size of 2 times m, where m is the number of iterations that we put in. And we have a maximum, or I chose a maximum of 30 for that, which was just reasonable. Okay, what do we do with this basis functions, or this, first this input vectors? We first orthonormalize them like this. And then we project the data that we have in this y onto these basis functions with this equation, and then we get from like hundreds of thousands of parameters to up to 60, which is kind of a big step. and we can go back from the reduced space to the full space also by just multiplying out with these basis functions or vectors. All right, now we know what gradient enhanced Kriging is, and in this flowchart, there's a bit more. So first we set up the surrogate model. This is what I said with setting up the covariance matrix and putting this data in. From there, we can calculate an exact Hessian because the space is so small. Now it's actually possible to calculate an exact Hessian, of course, in this model, in the surrogate model. And from there, we're doing a restricted variance optimization. And this is actually here, this variance is also an advantage of gradient enhanced Kriging, that we not just doing a restricted step, but a restricted variance step. So this variance is an additional threshold where we make sure that we are really going in the right direction. And after this step, we're having a new data point, and then we're doing micro iterations in this surrogate model to make sure that we're getting towards the minimum. And at some point, we are reaching a threshold where we can safely say we are at the minimum. And then we get out of the surrogate model by calculating the Hartree-Fock energy from this new data point. And then we're reaching a new macro iteration. And then we go on until we reach the actual threshold here. And then we are in the actual minimum of the orbital optimization. Okay, now I explained the subspace gradient enhanced Kriging. Let's see what some results are. I did a benchmark for this with small to medium-sized organic molecules and transition metal complexes. And this produced a benchmark of a total of 2,080 molecular systems with open and closed shells. So we have singlet here for the closed part, and then triplets and doublets for the open shell parts. And for my first task, which was this getting this different second order methods in with this Kriging, this produced this result here. So I'm gonna hit you with these numbers here. So these are the second order methods. The new one here is the BFGS. Here's the r-GDIIS, which is a new DIIS method also proposed by Roland Lind and his group. And then again, we have this RS-RFO. So these were actually already reported by his group and done by Sethio. And what are we looking at here? We have the averaged number of iterations for this benchmark. So we had this 260 molecules, and then we're getting calculating the average here. Then we have the standard deviation, the number of cases that have more than 120 iterations, and then some failed cases. Yes, and first to analyze again what was already reported, we have a kind of systematic improvement here by reducing every case here for this RS-RFO into this RS-RFO geek, reducing the number of iterations here for each case, as you can see. And so let's analyze my result here, which was the combination of BFGS and gradient. So here it would be Subspace Gradient Enhanced Kriging, and we compare it to the default method. So this is the most efficient one. And here are two cases where the method actually performs worse, but there are much more cases where it performed better here. And the improvement was about 12% for these cases here, and almost the same here for this worst cases. So overall, we could say that this was actually an improvement. So let's expand this table a little bit. Unfortunately, I made a small mistake or bigger mistake in my benchmarking, where I used here this maximum number of iterations that are put in the second order methods with a too big value. So we can't compare these methods here with these methods, which is a bit unfortunate. So this method here is actually what I have shown you here already. And now this is the new method here, which I also got working. So we also have DIIS with Kriging, but it has this problem with this value here. So but we can say for each case we have this systematic improvement using this Kriging. And I say here it's a quasi-systematic improvement because there are some minor cases where we actually again got a worse result, but those are just very small cases here with just an increase of 0.2, which is to be neglected. All right, so the second task was this getting rid of the prelude. And here I just want to show you briefly that didn't really work out. So we just started off here with the second order method with Kriging from the beginning. And you can see here that we in all cases got a worse result. But for example, here for the BFGS, it's actually not that bad. We don't have any cases that didn't converge, and also for this RS-RFO. But overall, it's still preferred to use this prelude. Okay, so a reason for this that this didn't work is that the Kriging actually has very little data in the beginning. And this is of course bad because we are starting here from the beginning. And then the second order method also doesn't work that well, far away from this minimum. And this also shows the dependence that the second order method has on the Kriging, or the influence. All right, let's come to a conclusion. I showed you Subspace Gradient Enhanced Kriging, and I hope that you learned something about it or got a more intuitive feeling about this Gradient Enhanced Kriging. And so I did a benchmarking for these different second order methods, and it produced a promising result. So for this BFGS combination with the Gradient Enhanced Kriging, it already produced a result that is preferred to just doing this DIIS. And yeah, and the second part with this prelude was not that for bringing that good results. But yeah, what remains is this competition between this combination of BFGS and Kriging and DIIS and Kriging. So you can look forward to this new publication that is coming, where we actually see if this is the new SCF procedure. All right, with this, I would really like to thank Roland, who welcomed me with open arms in Uppsala, and also Ignacio, his co-worker, who, as Roland always, gave answers to my many questions. And I would like to thank Hanrad, who nicely got into contact with Roland to make all this work, and Herr Dolk, who was the official supervisor for this module. Yes, with that, thank you very much.
Thank you very much, Daniel. Splendid presentation. Even I understood it. Thank you.
Thank you.
Any questions by anybody who is attending, please?
So I'm not sure. I'm not sure if I'm allowed to ask about. So, what is the cost of the method respect to speed up? Is there any gain in total?
So I didn't really test the performance of the method with respect to time, just with the number of iterations. But we can argument that the Kriging is not that costly because because it has this small subspace. And yeah, and that's why I would say the number of iterations, or the reduced number of iterations, is what is important here. And yeah.
Okay, I also had another question. So just for curiosity, is there any, let's say, so if you forget about Kriging and just do the Newton update, then you have if you have a quadratic region, then you converge in one step. Is there something similar for this Kriging, so that you have a certain, let's say, functional dependence where this Kriging brings you in one step to the correct solution?
So this one step is, of course, only possible for the quadratic, or a really pure quadratic function. But so
I didn't quite understand. Okay, this was too fast for me. So what is really the improvement of the Kriging? So I guess that is the integration of iterations from before, similar like the DIIS. But is there any case where you can they have a theoretical construction where you can say in this case it would perform optimal?
I would say it's just a relatively general method that really stabilizes the errors that we get from the other methods. For example, I showed before that when I have this high maximum number of iterations that we include in the second order method, the Kriging actually improves the method even better and this shows that the Kriging actually gets rid of this some of this numerical instability.
So I think it makes the iteration more robust, if I got it correctly. Okay. Okay, thanks.
Any more questions? If I may add and extend on your question, there's a sort of a fundamental change in what you're doing with the gradient enhanced Kriging, it is that you adapt your model to your data. When you have a second order approach, essentially every iteration you do, you toss over your shoulder the data you had from previous iterations. Here instead you have such that as the data points increase, the surrogate model will converge exactly to the parent model. That doesn't happen with a second order approach. Also, and I don't think Daniel sort of highlighted this, the gradient enhanced Kriging, you don't need any Hessian update methods for that part of the code. The second order code, which are used to feed the subspace, though, needs that. With that said, if the surrogate model wants to describe an inflection, a minimum, and a maximum simultaneously, it can do that as long as it has data to support that. Whereas with a second order method, if you now have data that supports this, your quasi-Newton-Raphson condition, which you base your update on the Hessian with, is going to be utterly confused and give you corrections that are just silly. So there are a lot of advantages, but you highlighted one that is very important. It's extremely robust. We haven't yet seen cases where this optimization fails. Whereas with standard DIIS, you start to go around in circles. You have the energy, you go down, 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 and then it jumps up, go down, down. And it's because that approach is, first of all, based on a second order approach. And secondly, it doesn't save the information it has acquired. So it makes the same mistake when it gets around to the same place it was before. It makes the same stupid decision and it goes around and around. And sometimes with the DIIS, convergence is just sheer luck or a random event, whereas the DIIS understands what's going on and, the GEK understands what's going on because it sort of preserves all the information. It is actually an exact extrapolator. If you go back to a point where you've been previously, the gradient enhanced Kriging will predict exactly the value you previously got there. So there are lot of advantages. Yes. Sorry, Daniel, for this. Any more questions?
So if there are no more questions, Roland, I would like to thank you very much for hosting Daniel for this internship. Thank you very much.
Oh, you're very welcome. I think Daniel had a question. Setio.
I just want to add about the times. So when we have this 2080 molecules, for example, for each subset, for example, singlet, triplet, for the s-GEK is adding about 30 minutes more expensive compared to DIIS. But it's more robust. Sometimes the DIIS is not converged, but the s-GEK is always converged.
And that was with the RS-RFO, right?
Yeah, correct. Yeah.
So that's the important thing with Mr. Wessling's report, is that he shows that we can use the cheaper DIIS or the BFGS procedure to get the step. And we preserve the robustness. And also, if you noted from the tables, the major difference between our new approach and old approaches are in the cases where we have difficult wave functions. So for the transition metals, the difference is significant. Of course, if you have kind molecules with simple wave functions, second order methods actually is doing the trick. And it's actually a surprise to us that we, even in those cases, could find a marginal improvement. But sort of the bottom line is, when it gets difficult, this method stands out as a savior.
Speaking of difficult cases, I'm working on a restricted OpenShell HF, and I'm not quite sure if you adapt it for transition metals. I have difficulty to converge with my methods. Does this method also adapt to OpenShell HF? Or what do you use for your triplets and doublets and whatever?
I think that's a question to Daniel.
Yeah. So all in OpenMOCOS automatically the unrestricted, I used unrestricted HF for the OpenShell systems, and yeah, this takes care of the OpenShell cases, and this is also automatically goes on for the gradient enhanced Kriging.
Could you adapt the code for OpenShell HF? Because there you have multiple diagonal blocks, because you have your occupied, virtual, also your active, and the virtual. Yeah. Because then you said in your presentation, you said you have your block virtual occupied, which hosts all your parameters. And if you adapt it to restricted OpenShell, you have 3 of such blocks. So in different methods use then 3 methods back to back. So you have what you do on one block, you do on all 3 blocks, and keep the order the same, and then this just works. So you could adapt it, I think, in your case, also to restricted OpenShell.
Okay. Yeah, I'm unfortunately not really familiar with restricted OpenShell HF, so yeah, that's why I can't really add to that.
It can be adapted. So as long as you have analytic energies and analytical gradients, and you have a good guess for the diagonal of the Hessian, which you use to design the characteristic length, as soon as you have these things for the parameters you use to define your energy function with, you're in business. And then if there's are couplings, the Kriging gonna see that from the gradient and energy information it gets.
All right, thank you.
You're welcome. Any other questions? Okay. Let's see now. I'm gonna pause the recording.